everyone, this video is about Darzens reaction. We also call it Darzens condensation or glycidic ester condensation. Now this term is basically based on the name of the product. Here I will focus on mechanism, application and diverse examples of Darzens reaction. Let's start. Here we can see alpha haloester or aldehyde or ketone as the reaction partner. Alpha haloester because with respect to this ester group, this is the alpha position and in the alpha position we can see halo. Chlorine is there, right? And in presence of base, we will get alpha beta epoxy ester. So from the color you can understand this part we are getting from this alpha haloester and the other side that we are getting from the aldehyde or ketone, and two new bonds are formed. Alpha beta epoxy ester, it is also called glycidic ester, and that is why we also call this reaction glycidic ester condensation or reaction. Fine. Now what type of bases we can use? Here you can see some examples of bases are there. So sodium methoxide, ethoxide, LDA, sodium hydride, and it may be Li or any other alkyl group. Now this reaction, it has some resemblance when compared to in terms of substrate. So why I am calling it so? Because when you consider Favorsky reaction, alpha haloketone is the substrate. So I have already made a video on Favorsky. You can check that. Right now the link will appear on the screen, top right corner. You can also get it on in the description box. Another reaction also there is resemblance, and that is Riefordt-Smetsky. There also alpha haloester is used, but the main importance is zinc is used, which we are not using here. So because of this similarity with substrate, there is some resemblance. Now alpha haloester, that is not the only reaction partner you can take. You can also take this type of compounds. Now it is not necessary chlorine, it may be bromine also, but the important point is this side you can see electron withdrawing group is present. Electron withdrawing group is required because we need this active methylene group, because ultimately we have to generate negative charge in presence of base. So next we will see mechanism. It will be clear how this negative charge is generated. So in this mechanism you can see in presence of base, negative charge will be generated by removal of this hydrogen. Now this negative charge, some enol can be formed. So this is the enol that is formed, negative charge, resonance. Now the next reaction partner, which is the aldehyde or ketone, whatever. Here we have taken CH3CH2COH. This aldehyde we have taken. Now this enol, it will attack from this carbon. C double bond will be broken. And now you can see there will be, so this part we are getting from the aldehyde, negative charge over oxygen, and this negative charge, now it can attack this carbon because chlorine will be the leaving group. So after removal of chlorine, what we are getting? We are getting three-membered ring, and that is the epoxide ring. It is the same molecule, it is just rotated so that it look better. And this is the glycidic ester, right? Now as application, we will see homologation of aldehyde or ketone. So this aldehyde you have already seen in the previous slide, that how in presence of this alpha haloester, how we are getting this compound as the final product, alpha beta epoxy ester, right? So this we have already seen in the previous slide. Now what extra things we are going to do, that will be the homologation. So homologation means carbon number will increase. Here we have 1, 2, 3 carbon, but ultimately we will get 4. That is the homologation. What we are doing now, that is the extra steps we are doing, NaOH hydrolysis. That means this CO2 now it will be converted to CO2 minus. So negative charge will be there because the medium is basic. But if you are acidifying it in presence of H plus, now O minus will be OH, and there will be, this oxygen will also be protonated. The next thing is removal of CO2, that is decarboxylation. So here CO2 molecule will be removed, CC double bond will be formed, and this carbon oxygen bond will be broken, oxygen will be neutral. So we are there is basically net removal of one CO2. This is the CO2 and this H will be removed. So it is minus H plus minus CO2. Decarboxylation, if I am numbering it 1, 2, 3, 4. So it is 1, 2, 3, 4. So at one position now we have this CO minus. Actually it is H. If I am already there is a proton, so it will be OH. Finally, so let me write it. Finally, there will be keto-enol tautomerization. So this enol that will be converted to carbonyl group. So here you can see 1, 2, 3, 4. So we have started with 3, but now if you do these extra steps after Darzens condensation, you can get homologation of aldehyde or ketone. Now we will see diverse examples of Darzens condensation. In this example, this is our alpha halo ester and we have taken benzaldehyde. Product is already given, right? But how it is generated? Negative charge will be generated at this position by removal of this hydrogen. Now this negative charge, it will attack here, and oxygen there will be negative charge. This negative charge will attack at this carbon and Br will be removed. And finally you are getting this product. Next example. Now cyclohexanone, that is see in the previous example cyclohexanone, and there is alpha position, there is bromine. But now in this aldehyde or ketone part we have taken this cyclohexanone moiety, and this is our alpha halo ester. So just like that previous example, here we will have negative charge at this position. We have taken base, and normally the solvent that is taken, that is the same. That is if it is potassium salt of tertiary butoxide, that is the potassium salt of this alcohol. So in the previous examples also you have to take ethanol as solvent. That is the same group. Fine. So in presence of base, this negative charge, now it will attack here. Negative charge will be over oxygen, and this negative charge, it will attack at this carbon. Finally Br will be removed and you will be getting this as the final product. Next example. Now in this case we have a pH group. And we have only one hydrogen. So this hydrogen will be removed and there will be negative charge. Formaldehyde is the aldehyde, or that is the carbonyl compound. So it will be attacking here. Negative charge will be over oxygen. Now this negative charge, we are getting this compound. It will be attacking here. Br will be removed. So finally we are getting 3-membered ring. Example 4. Now this is very interesting because it is not alpha halo ester, right? The bromo that is far from the ester, but it is allylic position. Now negative charge will be generated here, and this negative charge after resonance, it will that is next we will get extended enolate, right? So this is the extended enolate we are getting. Now this negative charge, it will make CO double bond again. It is shifted, and from this position it can attack this CHO. Now for simplicity, this part I have written as if it is R group. So when it is attacking here, negative charge. So it is better if we have some complex structure, we just simplify it. So I have here this R group. So it is attacking negative charge over oxygen. So this part is coming from the aldehyde, and finally oxygen carbon bond formation, bromine is removed. So what you will be getting? You will be getting something like this, CO2 Me, and here we will have R group. Now just we will get back to our R group. So this is the R group. So I have written it again. Same thing. These two are same, right? Next example. Now this is also alpha halo ester, but look at this. This group is you can convert it to R. Now once you have converted to R, it will be like this. Negative charge is here. These two are same basically, right? Negative charge will be here, and this negative charge, it will attack at this aldehyde OMe. So once it is attacking at this position, negative charge will be over oxygen. Now this negative charge, it will attack, Cl will be removed. So we are getting finally epoxide ring. Now we will get back to our R group, which is this one is benzene ring, another one is cyclohexane. So this is the R group. Otherwise these two are same, right? Next example. Again we have alpha halo ester. Now the left hand side part, alpha halo ester, it is simple, no problem. But look at the right hand side. This part you can simply convert to R group. So that is the most challenging part of name reaction. Suppose I am now discussing Darzens condensation. So obviously I will discuss examples from these reactions only. But when in exam, so many name reactions you have to keep in mind, and among all these you have to recognize, right? So recognizing part, the correct name reaction, that is the most challenging part. So here we have to understand that okay, this falls under Darzens condensation. So just when we are seeing this type of large structure, don't be confused. Just carefully watch that which part we should focus and which part is not important. So this part you can simply write it as R group, right? So here if we change to R, so this whole part I have converted to R, right? Negative charge is here. Now this negative charge, it will attack, and oxygen, there is negative charge. So rest of the part there is no problem. Now we will get back to our R group. So you have to again write this large structure, then only you will get the correct structure. So this is our R group. See, it is simply intact. So you can easily convert it to R group. Now this example is very interesting because it will not stop at Darzens condensations. There will be happening something extra. Now I will not go to the mechanism. I am simply showing you the Darzens product, and you know how it will be there, how it will be formed. We have already seen this mechanism several times. So there will be negative charge. It will again attack at this carbon where chlorine is present. You will be getting this epoxide, and this is the Darzens product. But what will happen extra? That is the question. So the medium is basic. So this hydrogen will be removed. Negative charge will be generated here. Now this negative charge, the epoxide is suitably positioned in such a way it can easily attack it, and the ring will be open because it is after all 3-member ring, not very stable. So if it is attacking here, this carbon oxygen bond is broken. Now numbering is very important. 1, 2, 3, 4, 5. So you will be getting a 5-1 connection will be there. You will be getting a 5-member ring. Now if you are thinking why it is not attacking at 4, because if it is attacking at 4, it will be 4-member ring. 5-member ring is obviously preferred. So it is attacking here, carbon oxygen bond broken, and once it is broken, it can take proton from the medium, and now this OH and this hydrogen together it can be removed, and at this position after removal of water you will get CC double bond, right? So see here, if you simply stop at this position, that this is the Darzens product, nothing extra can happen, it will be very straightforward. And mostly in exam you will get question which will not be so straightforward. Okay, so always check whether any further possibilities are there. This is not so black and white, right? So in options, suppose 4 options are given, and one of the options is this Darzens product. Another option is this is the actual product is given. So if you simply stop at Darzens product, if you are choosing that option, it will be wrong. So just see whether there is any other possibilities. So now simply let me do the numbering here. 4, 5. So at 5 position we have this COPH group, and this is the final product. So that's all about this video. So I will leave this video with a hope that it will give you some clarity. Thank you for your precious time.